and welcome everyone. My name is Andrzej. It's a pleasure to, well, virtually see you here. I don't even get your videos, which is quite awkward for the presenter. But anyway, welcome to my presentation called The Looms Are Coming, or The Course Are Looming. We are in the 315th day of the pandemic. And well, this is the Rzeszów Java user group, which I really was hoping I could visit personally because parts of my family are from around Rzeszów. So yeah, it would make a lot of sense and I would love to do it, but I can't. John, hi, good to see you as well. Now, some facts. I work at Revolut. I'm a principal engineer there. I've been there for a year, 3 months and a bit. So far, it's nice, but it's a startup. It comes with a lot of excitement, a lot of emotions every week. If you want to tweet me, tweet me. If you want to email me, email me. If you want to see my blog, which is kind of dead because I don't write too much there, then of course you're welcome to. But as I said, I don't write much there. Something about Revolut, if you're interested. This is the same marketing slide that you would see normally in many times. So I don't need to discuss it because this is not a corporate presentation. Obviously, Revolut is hiring. But yeah, let's talk about me a bit. I'm proud to be a Java champion. I'm proud to be old enough to have gone to JavaONE and have become a JavaONE Rockstar, which is the best speaker award in fancy terms. I ran GeekOn conference, which is hard to say because, well, last year we really couldn't do it, which is a shame, but well, hey, what can you do? Then Software Craftsmanship Kraków, Kraków Hadoop User Group, Polish Java User Group are the organizations I would associate myself with. However, I live in London now, but what can you do? My opinions are my own. That means if you disagree with something, I'm representing my own opinion. My mistakes are my own, not the company I happen to work for. If you have any questions about the talk, do write in the chat. And I'm absolutely sure that the organizers will mention to me that there are questions, and do it immediately you have them. If you would like to talk about something else, like Revolut, I'm happy to have a brief chat, but let's do it after the talk because, well, the focus is Loom and technology, not the workplace. And also, I like dry jokes because dry jokes are very important and very dry. I will try to make it a reminder for myself to drink something because I usually forget about it. So yeah, cheers. So let's start with episode 0 of our saga. Harry arrives at Utopia Planitia. For those of you who recognize the joke, good. For those of you who don't, well, you didn't miss much. Now, the question I wanted to start with is how many threads does your application run? It would be really awesome if we were in a room and you could scream or shout or anything, or even I could see anything in the chat, but I don't even see the chat, which is, I don't know who really made this application, but what can we do? So yeah, there is a chat. Yes. So 8. Or no, it's the 8, the factorial of 8. So yeah, that's a very big number. I think factorial of 8 is definitely a huge number. I don't think my application runs as much as that. But yeah, I looked at one of the applications I had access to within, let's say, the last half a year, and it happens to run 1,650 threads. Is it a lot? Is it not a lot? I would, well, I can give you the consultant answer. It depends. Also, if you want me to speak slower or repeat anything, just write it in the chat. I've managed to find a window and display it on my screen. What I wanted to show you here? Well, 1650 threads means 1650 times, let's say, 1.5 MB of memory, of operating system memory, just for the threads themselves. Is that a lot? Not really. Can all of those threads run at the same time? It's probably the question you wanted to ask. The answer to that is obviously not. However, for us programmers, it's just easy to make our applications in a way that will spawn more threads than will run at the same time. And it's absolutely normal. So let's have an example. Because, well, show me the code. Obviously, this is an absolutely production useless piece of code. It's an executor service-based Fibonacci calculator, which doesn't remember a thing, which means it is going to run extremely slow and it will be terribly inefficient. However, What it also shows is that there are certain problems that if you could write code like that, they actually fit the domain very well. It's just nice to implement it and not having to remember about remembering values, pun intended. So if we write it like that, obviously, if we do an executor that will spawn a lot of threads, this will take either a long time or actually never finish. But if we could just look at the semantics, it is easy to follow because the threads infrastructure doesn't get in the way. So yeah, now here, yeah, I'm a part of Oracle Groundbreakers. However, my accounts on their cloud ran out. So I wanted to mention Oracle Cloud in some context, and this is the only one that came to mind. Yeah. So when I try to run it, I got this very nice error in IntelliJ. That's actually mentioning blah, 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 failed to start thread, pthread create failed EA again. That's not E again, but EA again. For attributes, blah, 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 doesn't matter what there is. The important thing is there is a limit of threads that you can start in your operating system. It's probably much less than 8 factorial. It's probably much less than any other value that sounds big. So yeah, well, what is the exact value for that operating system? If you guess before I show you the approximate number, I think there might be a prize for the person who guesses. If not, don't worry, there will be an approximate answer given up later in the slides. So what happens? Where does the divergence come from? Well, we humans, we like to use threads as a notion of a unit of work or some amount of work, some activity stream, because that's how breaking down the problem into logical statements goes easily. And it makes perfect sense. We're humans. The first part of approaching the problem is breaking it down and then writing it as code. The problem is this clashes slightly with how machines, our favorite computers, even if you have the latest, greatest hardware from any company that starts with any letter, they like to have a thread that is mapped one-on-one to an execution unit, meaning a core. Why? Because that means that it doesn't have to do context switching. It doesn't have to worry about anything else. It just executes whatever instructions that thread wants to get executed. It's awesome. However, that means if you've seen a real application that wants to run 1600 threads versus, well, we don't really have a lot of 1700 core machines. Well, you can get some experimental machines if you're very rich and have good connections that have around 1800 virtual cores after hyper-threading, but it is an exception. Normal machine right now will have what? A desktop can have easily 8, 4, 16, maybe 32 if you got yourself a Threadripper, maybe 64 even. But that's the order of magnitude that we're talking about. If you're talking about servers, the orders of magnitude actually remain the same because the bigger servers come with a bigger price tag, and also people like to cut them into smaller places and smaller pieces, so they get more manageability, and the risk of failure and the impact of failure is actually slightly less. So a lot of threads versus not so many cores, which means, well, there is a divergence. And let's have a look at cores in general, because yeah, of course, having a multi-core machine in itself is actually running a distributed system. There is the definition of a distributed system that's famous. Everybody probably knows it already by Leslie Lamport. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. If you have threads, or correction, if you have multiple cores, and if you have imagine a heterogeneous CPU, so one that doesn't have all the cores the same, then this is exactly happening. If you look at a CPU right now, they will come with management engines and other things, which means your computer can break because a computer within your computer can break, can have problems. This is funny, but if we look at historically what happened, if you remember your first computer, I can remember mine. It was a 386, not exactly this picture. This is a random picture from the internet, but I started with a 386. That means that, yes, you can probably try to date me, not only using carbon processing. The important thing to look for when remembering history of computers is what changed over time. There is a very useful diagram and a data set that shows trends of microprocessor data. It's maintained at the address at the bottom right corner. So I took it from GitHub and it's attributed right there. So if you want the slides, mail me and I'll be happy to share them. What is evident is that A, transistors keep growing. B, frequency has plateaued around 2, 3, 4 gigahertz. So that's something we know. If you open up your MacBook, your, I don't know, phone even, the frequencies don't go to 5, 6, 7, 10 gigahertz. There is physics that's very stubbornly in place. The speed of light doesn't want to change, which means we have we hit a limit. What we also see is, that plateaued. We see that the typical watts from a CPU is kind of stable. Why is it stable? Because if you think about high scale, high volume computing, high density environments like data centers, cooling is actually a huge part of the problem there. If you want to deploy 100K servers, you have to worry about cooling. You have to do it efficiently. And if your thermal specification is 100,000 units of X watts of output, then if you change the output by 10 watts, this will distort the picture. This will not be in an equilibrium. And then you will have to adjust either by running less or replacing your infrastructure. And this is an investment, which means it comes with cost, which means processor manufacturers are kind of stable in terms of how much watts their products emit. Of course, I'm talking servers and machine scale computing. If you look at desktops, luckily they go, they try to get better and better at that. You can see it in the phones. You can see it with laptops. Years ago, it was unheard of to have a laptop that could stay on and do things like watch 4K movies for an entire day. Right now, it's the reality. Of course, I could say that a few years ago, it was absolutely normal to have a phone that can last a week, and now a phone that lasts a day is a rare thing. But yeah, let's not pick at the phone manufacturers anymore. But data centers, power limit, it's there. What we also see is after there was a plateau at speed, the number of cores has started to increase. This is because it is very important for us as a society to benefit from all the microcomputing that we do benefit from, to have access to more computing power, because that computing power manifests itself from a slightly growing single thread performance and multi-threaded performance or multi-core performance, which is just directly number of cores times the performance of that single thread. Right now, everybody's used to have a phone with 4, 8 something cores. I don't even remember how many my phone has. That keeps growing and that will keep growing. And to me, that's tremendously interesting, especially to us here, because I think many of you here will say that they are software engineers, developers, programmers, which means what we used to program with a single core in mind, now we will do with multiple cores in mind. How many exactly? Well, if we roll back 10 years, it was enough to have 1,280 cores to be on the position number 37 in the top 500 supercomputer ranking of this planet. 1,280. That's not a lot by today's standards. I could actually probably get it off eBay if I did a bit of shopping. Of course, those are the computers we're talking about but still 12,280 cores. That's not a lot. Right now, for comparison, or November 2018, the top machine had almost 2.4 million cores. You can see how many more cores that is. That's a huge number. And the position number 3, 10.6 million cores in a single machine. Of course, you can see that the frequency of those cores is somewhat slower, but the amount of parallel processing that is available is just incredible. The problem is you have to do parallel processing. And for comparison, clouds, today Amazon, it is absolutely doable. You just have to contact your rep, ask to get access to those machines, and you could get 400, almost 450 logical processors on a bare metal machine. Azure, what is that? 480 physical CPU cores almost 1,000 threads, so almost 1,000 virtual cores. That is a lot. Obviously, if you have that many cores, there is one thing that you will aim for. And this is exactly the kind of picture that you are aiming towards. You want all the cores that you're paying for, that you're renting or that you bought, occupied. If they are not occupied, if they are wasting, they are not doing anything useful, then why do you have them? You could have less and you would have less cost. You would be generating less energy and so on and so on. So the question is, how can we get there and how can we get there efficiently? And well, this particular machine had 2 terabytes of RAM. It was a very nice computer to work with. Well, we're multi-core. That's not a secret. It's 2021. Everything has multiple cores. Raspberry Pi has 4. A random fridge has 4. A TV has 4 or 8. A phone has 8. An Intel CPU has 10 or maybe 8 in the next generation because, I don't know, Intel cannot get things properly anymore. A consumer-grade processor, a Ryzen, has 16 cores, 32 virtual threads. A Threadripper, which is a workstation CPU, 64 cores. And that's something that I can go to Amazon or I can go to the shop, and normally I would be able to buy it just like that. Right now with the pandemic that we're all enjoying, it might be, you might have to wait a few days, but yeah, it's a consumer grade thing. You can buy a normal motherboard, you can buy the CPU, you can buy the RAM, assemble a computer and have one at home. It's doable. I know some of my friends have Threadripper based computers at home and they are very happy. Obviously, then there is the iPhone latest, let's call it, which has 16 cores. One common theme: multiple cores. Multiple cores are a thing, and programming for multiple cores is a thing. With multiple cores comes Amdahl's law. I'm not going to explain Amdahl's law to you in details here because it would take a long time. I'm going to show you a picture. The picture shows the speed up that we can get from a piece of code if we run it in parallel, assuming whatever parallelism is humanly possible for us. This chart goes to 65,000, depending on the parallel portion of the program. What that translates to if half of our program is parallelizable, so it can be made to run in parallel, we can get a speed up of less than 2. Because you have to pay the synchronization price. And if you have 95% of your program, which is perfectly parallelizable, you, with running that on 32 cores, you should be able to see the cursor, but I will not bet on it, so I will read the value. You can get a speed up of slightly, somewhere between 12 and 14. That means one thing: 32 cores, 12 to 14 times speed up. You can also see from the shape of those curves is that the biggest growth, the biggest incline is at the beginning. This is probably why, if you're doing multiple virtual machines, they are probably 4, 8, maybe 16 cores, because to keep growing efficiently in the, let's say, 64 to 128 core or beyond region is more difficult. It's cheaper, easier to run 2 machines of smaller size, or even 3, and then if one of them fails, it's just cheaper to replace them because you don't have so much traffic, so many things to replace. Of course, if that's supported by your domain, because if you need a big server, sometimes you just need a big server, you need a big computer. Why is this relevant? We talked about this area. This is where the efficient growth happens. Later on, different portions plateau, some faster, some later, depending on how much parallel can be run. And what do you do as programmers? Well, it's easy. Ideally, you share nothing. You do small instances of the same application. You scale dynamically. I'm not going to speak like a cloud vendors, maybe even saying serverless somewhere. But the ideas to cutting big problems into small ones are nothing new. It's people have been thinking about solving those problems efficiently since the 50s, 60s, 70s. There is a lot of paper. Right now, we also have easy access to hardware that can help us with that. And if you're terribly tired and don't want to listen to me anymore, or just want to switch mentally off or need to go for a coffee, your modeling exercise that can be your takeaway number. 0 is if you have a problem that you're doing with a traditional approach, you could try using Akka, you can try using Vertex, something that offers independent processing of, let's call it independent processing, and try to model your sequential problem using those. You will have fun, but this will be a useful mental exercise that will come useful later in the future to come, sometimes sooner, sometimes later for them. But then you can say, but I already have a system. And if you already have a system and it's not that easy for you to rewrite it into a completely new paradigm, then you have a bit of a problem. Because, yeah, with many cores comes, well, there's one more thing that comes with many cores. This is what a server or a workstation with 2 physical CPUs might look like. Might look like because the layouts differ depending on the provider. The patterns stay the same. You will have 2 physical CPUs, obviously, and you will have memory associated with CPUs. You can see that there are pairs of sockets close to the upper and bottom and lower processors. This means, well, this is explained by one thing. Not all memory is considered equal, or there is something called NUMA, so non-uniform memory architecture, that essentially means that if you're in CPU 1 and you want to access memory that's closer to CPU 0, you will have to go through CPU 0, which means latencies of accessing RAM, the one that you're used to so much, to treating as almost cheap instant cache, are actually not the same. It's very easy to forget about if you don't work with a multi-CPU system. Or even some of you might get into that if you have a single CPU, single physical CPU system that actually behaves like a NUMA-enabled system. So like it had multiple physical CPUs inside. So NUMA, something that you might want to read about. And yeah, I mentioned CPU catch. Where's the catch? Well, the catch is obviously here. This is an architectural diagram of Core i9 10900. Obviously, it's visible at the first glance. Do you need to study CPUs now? Well, yes, no, it depends. Well, not really. You don't have to. Where the problem is it is here. All the cores, all the processing unit have a gateway to the rest of the world. And part of that gateway is obviously I/O and all PCI Express slots, but part of that is your memory interface. In this specific case, you can see that it's dual channel and it's DDR4, and all of the cores have to share that resource. And that resource has a bandwidth. Now, I said that you might have a processor, a single die processor, a single enclosure processor that behaves like if it was physically multiple CPUs. An example of that is a Threadripper CPU, which comes with CCD. Well, I forgot the extension of that abbreviation, but it comes with units that all have 8 cores. They are connected through Infinity Fabric to memory controllers, which means if you want to talk to memory from this guy, you have to first cross the Infinity Fabric, then you talk to the memory controller, and then if you want to talk to another core, so it would just might so happen that it's located in a different compute die, you will have to cross the Infinity Fabric again. Of course, crossing those fabrics, crossing anything while doing anything on a CPU takes cycles, which means there is latency inherent. This is how not having to share, not having to synchronize actually allows you to go faster, because you don't have to wait, you don't have to ensure that everybody's doing things in an agreement. If you can divide and everybody pushes forward in their own fastest pace, and then at the end, if there is one person that, for example, receives all the results, then that is going to work very nicely. If you have to agree, if you have to synchronize, that costs cycles, and that costs milliseconds, and that costs latency. Takeaway, a small takeaway now. If you're running software on anything big, or if you're running software on anything non-trivial, something like, well, multiple physical CPUs, I would encourage you to test on the architecture you run. Why? Because you might get unexpected concurrency bugs, that you cannot discuss and discover even on, for example, a laptop or a MacBook, or it might be extremely hard. If you're doing pure functional programming, maybe you're covered, but for the usual casual imperative systems, if you have to do low-level concurrency, I would encourage you to test on what you want to run on a similar class of hardware. It doesn't have to be exact. Of course, it's nicer to be able to, but if you run on a 2 CPU machine, test it on a 2 CPU machine. You might be surprised. And then there is one more extra thing there, memory bandwidth gap. That's a gap between the speed of memory and how it's growing compared to the performance of CPU and its growth. You can see that there is a gap, and this gap keeps increasing year by year. Why is that happening? Because, well, CPUs did the easy thing. They started adding cores. We already know that the speed expressed in gigahertz has plateaued. What keeps increasing is the number of cores, but we still talk to the same RAM or very similar RAM. There might be slight increase in the frequencies. There might be slight increase in CL speeds, but ultimately, it is not going very, very quickly. Somebody could now say, but hey, yeah, we are trying to work around it. And I will say yes. You remember the Intel CPU that mentioned dual channel memory, which means you can talk to two memory, let's call 2 memory sticks at the same time. You can look at current AMD processors, which will benefit from having 4 memory sticks. I'm oversimplifying here a bit, but it should convey the message. So they can talk to 4. Then some of the recent Intel server CPUs can, at the same time, exchange information with 6 memory banks. And then recently, I think, recent Threadripper Pro workstation CPUs have announced 8-channel memory support, which means, yes, we're trying to work around that gap because the gap exists and the gap is there. And that means we need to be able to feed the processor with data fast enough so that it doesn't run out of things that it has to process. Otherwise, it's sitting idling and doing nothing, and that's not really useful. And here, I will mention this. It's a chart that keeps being updated on the internet. It's called Latency Numbers Every Programmer Should Know. They give the reference order of magnitude categorization of very popular, very frequent things that you might be dealing with. For example, an L2 cache reference is 4 nanoseconds, an L1 cache reference is 1 nanosecond, so 4 times faster, whereas L3 cache reference I cannot even see in this chart. However, one main memory reference is 100 times L1 cache. This is why memory gets through different layers of cache. This is why your CPU will have multiple megabytes of L3 cache, some megabytes of L2 cache maybe, and lots of kilobytes of L1 cache, because accessing memory, you cannot do it directly. And within a nanosecond, a processor will execute some cycles. That's what you are going around. And then you'll see SSD reads, which take 16,000 nanoseconds. And I don't see NVMEs here. So yeah, let's go around it. The bottom part or the bottom line of this part is, because we have multiple cores, because they have to agree and they can of course disagree, they can be impacted in bugs happening elsewhere. Every system, even a single computer, starts behaving like a distributed system, because you have exactly the same effects that you would before observe only in distributed systems. We get that in our desktops. We get that in our phones. So developing an intuition about treating systems like distributed systems will go forward a long way. And then we can talk a bit about compute location. That's something that's going to change us with the world as we go along. We're used to processing on the server, right? Hey, I've used the term server myself with respect to hardware. What has to happen is the increased quantity. So all the IoT devices, the smart fridges, smartphones, and smart everything else, and their computing capacity will shift some of the compute towards the edge. So your fridge will do some processing to order whatever it wants to order, or your phone will try to do some pre-processing before it uploads the data or it syncs the data. And that means that there are going to be very interesting security concerns as well, but that's a side note. How does it affect me, the mobile engineer, or the engineer in general? If you look at a mobile engineer, so somebody who's focused on writing software for running on mobiles, that means that they effectively have to learn, or maybe they already know it, but they will have to utilize multi-threaded, skills that are typically associated with backend engineering. That's just what happens. Threads are a thing, and backend processing is a thing, and more processing done on the mobile means it has to run well. Front-end engineer, well, that person can say, hey, I have my Angular, Vue, React, whatever framework of choice is there, but browsers come with web workers. They come essentially with what looks and behaves like threads very much, which means they have to become aware of those paradigms as well, because they will be doing processing. Otherwise, your Chrome browser will, or your other browser will just freeze and work sluggishly, because otherwise this is what we end up with. And backend engineers, we're actually not in a bad spot. We've been made familiar more and more over time with this, but last year, this year, and the years to come will bite even harder. Now, we talked about this. We already agree. I drink now, and with multi-core, with the approach in which a lot of the processing happens in multiple places at once, you will need to exchange information. The information cannot be exchanged or treated uniformly. You will have to exchange it in quants. The quants are usually called events. So look at events and event-driven architectures. And of course, I already mentioned this, papers from 60s, 70s, 80s, some of the links are available here, are a good thing to start reading if you haven't already. You will learn a lot. It will hint at a huge number of subtle bugs and not so subtle bugs sometimes that you might find very interesting. Now, if you want to write software for those modern computers efficiently, and you don't just want to listen to the cloud salespeople, explore alternative concurrency models. That's something that you will have to do if, of course, that's the area of software that you enjoy doing. Loom is one of those. So now we can go on to area number 2, which is going to focus more about Loom and show you and talk about Loom a bit. The same picture that you've seen before. As I said, this is a reminder for me to drink. Project Loom. What is Project Loom? Project Loom is fibers and continuations in Java. It's a well-known fact that any problem becomes a completely different one when you add in Java. Same goes for fibers and continuations. Now, a brief reminder about threads. Threads in Java currently map one-to-one onto operating system threads. It used to not be the case, because back in Java 1 days, it used to be green threads and so on and so on. Threads in Java are reasonably expensive to create. As I already mentioned, a rule of thumb number of 1.5 megabyte per thread. They also cost time because it takes a lot of operating system activity and processor cycles to create a thread. They are expensive to use if you want to use multiple threads at the same time, or if you want to switch. A context switch is an expensive operation. That's just the way it is. This is how operating systems are implemented. And also threads come with limited populations. I hinted at this already, but this means that we have to adapt our software to the limitations of the framework that we have to work with, which means in the context of threads, we cannot express certain algorithms using threads just in a plain old way. We have to come up with things like tasks or some sort of an intermediary, because if we try to express, for example, the Fibonacci sequence that I've shown you before with threads, it would break badly. There is a good presentation about threads that I can recommend. It's not by William Dafoe, it's actually by Adam Dubiel. You can find it online. I'm not going to go through it. But if I try to do something like this, and I can try to do it on a laptop, I can try to do it on a workstation. Well, when I try to run it on a a Linux workstation, I got this. When I tried to do it on my MacBook crashed and never went up. Or actually, I had to power cycle it for it to restart, which means there is some limitation connected with creating threads. And look at the algorithm. It's doing nothing fancy. It starts a thread that just increments a shared counter, and the thread gets garbage collected. Magic. Nothing there. Why would it not work? Well, that's the problem. If you start creating threads very aggressively, you will get problems. Somebody could ask, hey, but what is the limit? Is there a limit? The screen here shows 102897.3 as the value of proc kernel threads max. If you're worried about which system this comes from, it's my own workstation. And yeah, I've been using this with Linux with success for a few years. So if somebody tells you that 2021 is not the year of Linux on the desktop, I will continue to disagree. So I tried in a bit more brute force way to narrow down the rough number of threads that I would actually be able to spawn from that operating system. And I ended up, well, the last value that I succeeded in reading was 1744 threads. After that, Java failed to spawn, or anything else to spawn has failed, with unable to create native thread, possibly out of memory, or process resource limits reached. That's running with the settings that my system runs. Of course, it is possible to tune the kernel parameters for it to go further. The takeaway here is an operating system comes with limit to native threads. Even on a 128 gigs of RAM machine with 60 almost cores, you cannot create 100,000 threads. It's just either very hard or just plain old impossible. I tried it a few times. This is the only time also that I managed to capture a screenshot, because once you get very close to this limit, it takes time for the operating system to switch between those, all of those thousands of threads that are running, which means I couldn't even take a screenshot of at some of the other attempts. And now, something just switched focus on my operating system. How is that happening? Yeah, so now enter Loom. I do something almost the same as before. I do this. I do thread instead of start, but I do start virtual thread, and this finishes. And somebody could say, why is that? The answer to that is very simple. This is using Project Loom. What Project Loom does is fibers or virtual threads. So threads that do not map one. How long does it take to finish? As in this calculation, it's rather simple, and I would say I can run it towards the end of the talk, and we should be able to see, and then I should be able to give you an answer. But let's say in orders of seconds rather than minutes. This works. Why? Because it doesn't spawn this many operating system threads. What Loom does is it creates virtual threads, or it exposes a virtual thread API that talks and looks exactly like the thread API that you know in Java, and it does the intermediary of mapping them onto operating system threads, or actually Java threads, which are then mapped onto operating system threads, which means you don't deal with such heavy low-level constructs anymore. Now, why would I worry? The reason is because, for example, we very frequently deal with blocking synchronous code. And there is nothing inherently wrong with such code. Of course, the reactive followers will say that all blocking synchronous code is bad, but hey, we have a lot of it, and fixing it and improving it will take time. Sometimes which we don't have. Sometimes we just have to deal with a system that's just blocking synchronous and very sad, but this is what it is. So this style of coding fits some problems very well. And if it fits a problem well, then why should you change your approach? Second thing is, if you do blocking calls, you might get you probably will get suboptimal resource usage. You could improve it by doing asynchronous calls, but then asynchronous calls sometimes might complicate the code. Let's have a look at a picture showing the idea, not an actual code example. So imagine you're a system. You're running in a Linux, obviously, and you want to do an operation which involves talking to the database, calling another microservice, calling a very slow microservice, and then you have your result. So when you issue the call to the database, the time wasted by your thread until the database returns is wasted because your thread does nothing. It's waiting. When you talk to the microservice, you waste processing resources because your work should be doing something else. Well, your course should be doing something else. When you talk to the very slow microservice, it's even more waste. And of course, because it's slow, it's going to be even magnified. What can you do? Well, you can try using non-blocking APIs, which are a necessary thing, and they have been a necessary thing to increase utilization. However, if you started and explored Java and I/O, you know that the paradigm there is slightly different. They are harder. They are harder on the human to get friendly to the machine. And it's a fair statement. You don't have to feel super comfortable around Java and I/O because their difficulty is a thing. They are harder to debug because if you want to get a reasonable stack trace out of non-blocking asynchronous APIs, well, sometimes I will say good luck. They are hard to profile. They are hard to understand thoroughly. If you have a number of asynchronous processes happening at the same time in a system, how can you say how long one took exactly? Distributed tracing, it's a thing that it's very popular if you look at YouTube, but it is a difficult thing to have. And they also do one most cardinal sin, in my opinion. If you look at yourselves as programmers who are trying to solve real problems with code, they require remapping a problem that's usually linear onto something asynchronous, onto machinery. That means you are leaking abstraction because the computer forces you to write code in a certain way, in a very specific way, because otherwise you sacrifice any efficiency. And then there is the issue of callback hell. This is one of the styles of writing asynchronous code, which is you write code that does a lot of callbacks. And that was a style that was particularly popular in JavaScript. And I will not pick at this language in any way right now, because why would I? The problem is you can get to similar things in Java or any other reasonable language as well. The problem is you issue a function, and then this function will do a call, and an argument to that call will be a callback, and then in a callback you will have another callback, and then trying to debug this is a nightmare. Trying to rewrite this to something that looks reasonable, it took us, the industry, some time to figure out what is the correct way to approach this. However, with that, at least we weren't blocking. So you remember this example. This is a casual Fibonacci sequence. Nothing really useful, but it demonstrates the idea. It is very easy to write it based on an executor, because the task of getting the previous and the previous value of the Fibonacci sequence it's a well-defined thing, and you can just ask an executor or something hidden, something in the background to do it for you. And now the big difference is, what if I could make creating 3 threads cheap? Well, that's where Loom comes in, part 2. How do you use Loom, or what is the Loom? What is Loom from a user's point of view? You, as the developer, want not to run operating system, not to run classic Java threads, but you want to run Loom threads. The difference is extremely subtle, and the difference is this. So instead of running, for example, thread builder daemon factory, I do thread builder a virtual factory. Why? First reason is all Loom threads will be daemon threads. And how do you know it's a Loom thread? Because it uses the word virtual. So a virtual thread is a Loom thread, and that's all there is. You can also start it with thread start virtual thread. It will be started immediately. You cannot create a virtual thread and not start it. You could give it a latch or some sort of a barrier before it proceeds further. But this is how you start it. This API is extremely limited on the surface. So this is by design. It should be simple, and it should not be, you shouldn't have to get a PhD at least to be able to use it. You should be able to do minimal code changes, and it should look like exactly the APIs that you're used to for you to be able to use it. So it's very simple. How can you tell whether you're dealing with a Loom thread or a native thread? Well, there is a method on the thread API that says thread is virtual. And if you want to react differently, then you can. But so what exactly are those virtual threads? Well, technical term is fibers. They are implemented natively. Natively, as in they are provided by the JVM. This is in opposition to some coroutines or fibers provided by the compiler or by some libraries, which some other languages at the moment do. It is my expectation that some of them will migrate to Loom as soon as the opportunity presents itself. However, this is not now. And also Java fibers coming from the JVM have the huge benefit of being fully integrated with everything that you're used to on the JVM. So blocking, locking, collections, exceptions, stack traces, it all works. Some of you might have worked with Quasar before. Project Loom is, in my personal opinion, Quasar done right, because for it to work right, for it to behave correctly, it has to run on the level of JVM. It now is. It's a project that's running within Oracle. So, but then somebody could say, yeah, but I can do something stupid like this, and I can put a thread to sleep, and that throws away this virtual thread, and what then? Or blocking, or any other operation that would render a normal thread useless. This is where the benefit of Loom being implemented on the JVM, at the JVM level, again comes to play. Sleep, blocking, most of the necessary operations have been enriched by Loom awareness. So you can see, for example, sleep now is checking if a thread is a virtual thread, and if a thread is a virtual thread, this will do something else than a classic sleep method. You will find descriptions and, well, examples of such modifications everywhere in the JVM if you care to look. However, well, what's under the hood? Well, under the hood as of now is an API called continuations. And here I have to say I'm very disappointed, but, well, not disappointed. This is a fact of life when dealing with things that are in progress. This API is not going to be made public, or in a recent email on LoomDev mailing list, there was a message that you are not going to, as normal developers, you're not going to be able to deal with continuations, which means at first, it was supposed to be possible, or I was hoping that it would be possible for us to deal with low-level fibers and coroutines interacting and define our own continuation scopes and have a lot of fun there. The problem, as of now, it doesn't seem like the case. It was supposed to give us pinning and unpinning, but it's all work in progress. And as I mentioned an email, this is a screenshot of this email. So if you want to verify that it actually exists, at least existed in my Gmail, you should replace use of continuations with virtual threads, and continuations will not be usable directly. They are now in the early access, but the class will be removed, which means sadly this single email made a very exciting part of my presentation obsolete, so I decided to delete it. So yeah, but it's not going to be there. Now, that leads us, sadly, to questions, or, well, not sadly, but to questions nonetheless. First question that you should be asking, or third question that you should be asking, or second, depending on how you count, where can you find Loom? If you want to play with Loom, what should you? You have to go to jdkjava.net/Loom, download an early access JDK. As of now, it's JDK 17. And you can play with Loom only there. There is a whole wiki, there are mailing lists that are dedicated to Loom. If you look at presentations, if you want to try to migrate some algorithms, you might have a lot of fun. You might also discover some bugs. You might cause kernel panics. You might crash your operating system. It's work in progress, and it's low level, and they are building it. So bugs will happen. So the second question is then, how should you build an intuition about working with such multi-core system? How should you try to approach building software for modern architectures? Well, the simple answer as of today is you should get yourself a multi-core machine, not a MacBook, but something that has 2 physical CPUs, and run, well, have fun. Do benchmarks, do nonsense stuff like running Fibonacci. See what happens. Try to measure it. Try to benchmark it. Get under the hood. If you get an old one, not only is it cheaper, but it also all the effects are magnified, so you will be more exposed to it. Now, Loom, it's great, but will you use it? And here is another answer that I'm not the happiest person giving, but most likely Loom will be directly used very heavily by framework and library builders, curious people, and students. So if I look at me in the reality or in the context of an enterprise or a company that does business software, it is most probable I will not have a lot of opportunities to play with Loom. Not directly, because it's probably going to be shielded by Netty or by Jetty or by any other, let's say, HTTP glue interface or TCP glue interface that's going to do the low-level things. Those people, the framework constructors, the library constructors, they will use Loom directly. They will, and they already have started rewriting their applications onto Loom. Students, obviously, because there is going to be a tremendous amount of very interesting research when there is a generally available, very popular, very well understood language that exposes some fiber and continuation concepts out there. I'm saying some because work in progress, what's available will change versus what will ship in the final version. Another question is, should you use Loom in production? To that one, there is a simple answer: not right now. It's not fully stable, and it's experimental. It's early access. Things will break. Nobody will give you any guarantees. You cannot. I am not aware of you being able to even approach Oracle to get any support for Loom as of now, which means if you want to make something important run on Loom, it's probably not a good idea. I'm saying probably because maybe you have an area in which failing occasionally is worth the effort and is worth the experiment, but probably not yet. Sometimes, or when I still used to do some of those sessions in person, somebody would usually ask me, how do I get all the fancy colors? The answer to that usually was use a plugin called Rainbow Brackets and enable semantic highlighting in my favorite IDE, which is IntelliJ. If you use Eclipse, I have no idea. And yeah, that sadly finishes the presentations. So are there any other questions that I should answer? Is it true that the virtual thread in Loom project has got the copy of stack, each of them? No. Okay. Questions are incoming. So I'll start with John's question about how long does the Loom piece of code take to execute. So there are two answers to this. If I look at the Fibonacci example, the Fibonacci, if both versions were able to complete, Loom was usually slightly faster. Why? Because I did what I very frequently see in code, and I did executors new cached pool without specifying a limit, which means that means that new threads will be created if there are none available, which means that there is the overhead of creating new threads. If I put a boundary, Loom is still slightly faster. The order of magnitude observed on a 56 core machine was around 6.6 seconds or 6600 millis to compare to 6900 running direct threads. So not a massive difference, but you can see a difference. My intuition, because I haven't explored it thoroughly, is because there is less context switching, because there are less threads being created. Happy to talk in more detail later. I was taking some screenshots. Would it be faster if you run it a second time? Yes, I did run it multiple times. I wanted the JVM to heat up. But how much exactly? Well, we can always design an experiment and try to run it. So yes. Now, virtual thread in Project Loom, copy of the stack. That's difficult because, well, yes, stack trace and stack traces in Project Loom have to work. They have to work the same way that you're used to them running, which means they will originate from a specific place in the stack, and they have to then build upon it. And this is why it's this is part of the effort, making it transparent, making them work identically, irrespective of whether you're running a native, not a virtual thread, versus running a virtual thread. Whether it's a full copy of the stack or is it just a pointer, I will not say as of today from the top of my head without consulting the source, because that source code, that base changes, and I don't want to misguide you, sir. So sorry about it. Now, Jacek, how would Loom influence presence of actor model among enterprise applications? Would it have any effect, or this not related? First of all, if you look at Loom virtual threads, I personally find them very, very matching what, for example, Akka does. I would expect somebody will try to implement an actor per virtual threads very, very, very quickly, because it maps almost naturally, or it feels like it maps almost naturally. I've never tried it, but it feels like a good idea, which means if I think it, then anybody else probably thinks this as well. Now, will it influence the presence of actors in general in enterprise applications? It's a completely different story. This approach will have a very efficient, very well running. It already is very well running and very efficient. The development tool or just a mechanism of approaching building software. The problem is people have to understand it, and it's slightly different to what they are used to. So if you ask me, I would expect people would probably try to use the synchronized and whatever other constructs they are used to, but they will use them on top of Loom, which means they will be able to freely create those 1600 threads that I've shown you. I've shown you at one of the first slides, and that through the magic of Loom will be only, let's say, 60 operating system threads, or maybe let's even say 128. And that's already going to reap and deliver huge benefits. I would love for actor model applications to become more popular, but so far I have not seen it happen, primarily because people have not been taught in that way, or maybe it's the casual approach that is prevalent in the industry or in educational circles. I would love it, but I don't see a huge game changer just because of Loom people suddenly jumping to actors. It would be great, though. Now, there is one more question. If we map a virtual thread to actor, it would be easier to explain to developers. How does it work? Yes, absolutely. I agree with you here. And I would expect similar things go to, for example, Vertex or any other frameworks that are strong proponents of isolated, isolated fiber-like execution. It makes perfect sense. It reduces the surface in which bugs might happen. But if you wanted people to communicate with actors properly, they would have to have a mailbox or exchange messages. Whereas people like calling methods and waiting for those methods to return, because that's how they map what they map the problems onto. So yeah, I would like that to happen, but it requires a mind shift. On the other hand, if multiple threads of execution become a concept that is very common and very natural and much more adopted, then I see that as possibly a stepping stone towards further Loom adoption. Further actor adoption. But yeah, I would love to see it.